Hello and welcome to my new video. Today we will have a closer look at four important concepts: obfuscation, encoding, encryption and hashing. What they are, how they differ, and how they are used in Android applications. I would also like to note that this video will be useful not only for those who are interested in reverse engineering, but also for usual Android developers, since this topic is quite often asked in interviews for Android developers position. I personally had such experience several times. Also, I have prepared some sample applications so that we can see how these techniques work and how we can reverse engineer such applications. Obfuscation is a common technique widely used in Android development and in software development in general. It's the process of modifying class names, variable names, and sometimes even the app structure to make the code hard to understand for reverse engineers. Both legitimate and malicious developers use it. Attackers use it to hide harmful logic, while legitimate developers use it to protect the sensitive code and data from being stolen. In fact, Google's official documentation recommends using obfuscation as a part of app hardening to protect application from tampering and reverse engineering. Obfuscation can be done in several ways in Android. The simplest way is using ProGuard or R8, which automatically renames apps, classes, methods, and variables to meaningless names. Some applications go further and use custom obfuscation, manually replacing names and strings to random symbols. For reverse engineers, obfuscation doesn't make analysis impossible, just slower and more confusing. When you see unreadable class names or strange function calls, that's a strong hint that the code has been obfuscated. Now let's look at encryption. Encryption is a process of transforming readable data, plain text, to unreadable data, cipher text, using a specific algorithm and a secret key. Without the correct key, encrypted data cannot be decrypted back to its original form. Encryption is mainly used to protect data from unauthorized access. There are many encryption methods, from very simple ones to advanced cryptographic standards. Some examples of encryption are Keyser cipher, AES, and RSA. We will see examples of some encryption methods later in the video. Now let's proceed to encoding. Encoding transforms data to a different format for compatibility and safe transportation, for example over the internet. Unlike encryption, encoding is not meant to protect data. Anyone can decode it easily back. However, some developers sometimes use encoding to slightly obscure strings and make it harder to find them in the code. For example, hiding URLs so that they don't appear when you search for HTTP in the application's code. Common encoding methods are base64, UTF-8, hex, and URL encodings. We will have a closer look at some of them later in the video as well. And now let's discuss hashing. Hashing uses mathematical function to transform data into a fixed length value called hash. The key property of hashing is that it is one way. You can hash data, but you cannot reverse it to get the original input. Hashes are often used for data integrity and verification. For example, servers store the passwords not in their original form. They are kept hashed. When the user logs in, the server hashes the entered password and compares it to the saved password. And if they match, the login is successful. So typical usages of hashing are integrity checks, password storage, message authentication, and files identification. Common hash algorithms are MD5, SHA-1, SHA-256, HMAC, bcrypt, scrypt, and others. We will also have a closer look at some examples of hashing later in the video. Now let's proceed to the practical side, where we will slowly, step by step, consider all above mentioned techniques. We will start with obfuscation. For the beginning, I've created a very simple one-class application where you can see several methods that create string and int values which are set as text values and text use. From the developer's side, these methods look very simple with understandable names. Let's generate an APK and have a look at how this code looks when we open in JDEX. We can see that most packages still have normal names, and we proceed to our package. We open main activity and see that the code actually looks very similar from both developers and reverse engineers' perspectives. However, many local variables were removed or inlined. For example, variables inside methods were removed, sample unused variable in onCreate disappeared, and sample used variable was inlined directly into the log call. That happens because of code optimization performed during the build by R8 or ProGuard and later by dexing, which applies optimizations and inlining. That functionality is on by default, and you generally cannot and have no reason to switch it off. But most of your code remains the same, methods name are still present and so on. Now let's have a look how we can enable obfuscation. In Gradle build files of our app module, under Android build types, you will see minify enabled. By default it is false. Setting it to true enables code obfuscation, shrinking, and optimization. And also note this line: get default ProGuard file, ProGuard Android optimized.txt. It means that build uses the standard Android optimization rules. And just a quick note here. Even though we see the word ProGuard in the Gradle file, modern Android builds actually use R8, which replaced ProGuard a few years ago. R8 performs the same tasks: code optimization, shrinking, and obfuscation, and it still understands ProGuard rule files. So whenever we talk about ProGuard rules or ProGuard config, we are really talking about R8 reading those files. Let's now generate an APK and open it. First, let's take a look at the app structure. You will see many packages with non-human readable names, letters and numbers. Remember, our sample APK contains just one class we created, main activity, so these packages are obfuscated generated code for libraries and SDKs. This is why there are many obfuscated packages. You may ask why system or library packages are obfuscated, but main activity and the app's package name are not. It's because the standard keep rules preserve classes referenced from the Android manifest. Because the manifest cannot be obfuscated. If main activity was renamed there, the system wouldn't find it and the app would crash. Let's now look at our class. Here much more code was inlined and many of our helper methods were removed. That happened because the build used ProGuard Android optimized.txt and aggressive optimization removed or inlined simple code. Since major part of our code was simplified, it's harder for you to see how obfuscation changed the names. To see obfuscation more clearly, we will switch from ProGuard Android optimized.txt to just ProGuard Android.txt in Gradle. This uses less aggressive optimization and will not remove or inline our small methods. Let's create a new APK and open it again in JDEX. The default generated code looks similar and package names are obfuscated in the same way. Let's inspect the main activity again. Our methods were not removed because of optimization, and now we can clearly see how obfuscation worked. Method names are no longer readable and are replaced with short identifiers like C0, D0, and so on. That's how basic obfuscation works. Of course, this app is very simple and remains easy to understand, but I intentionally made it simple so you can clearly see the mechanics. For production apps, obfuscation makes reverse engineering much harder, especially when the app is large and call chains are complex. Now let's look at one more thing related to obfuscation. In the Gradle ProGuard files method, we also see the reference to ProGuard rules.pro. This is an automatically called file present in every Android project, unless removed manually. This file can be viewed from the Android project files menu, and if we open it now, we can see that it contains standard comments explaining how to use it. Generally, this file is needed to make exceptions for obfuscation. For example, to specify classes or packages that should not be obfuscated. You should never obfuscate logic related to serialization, because if it gets obfuscated, it will not work at all. That is because serialization requires exact matches in classes and fields names. The same applies to the code which relies on reflection. One more thing that can be done in this file is defining custom rules for obfuscation, and we will now look how it works. I created and put 3 text files in the app folder: classes, members, and packages. These files contain thousands of randomly generated gibberish strings, which will be used by R8 or ProGuard as obfuscation name sources. Now let's create an APK with these rules and inspect it. When we open this APK, we immediately see that most of packages are heavily obfuscated. If we open any random class related to automatically generated code, we can see that the identifiers look gibberish and it becomes difficult to read the code. Even our simple activity now has methods and classes names which are hard to read. From my experience, legitimate applications are usually using standard obfuscation settings, while custom obfuscation is used by malicious applications trying to hide malicious logic. So we have covered obfuscation, and now let's move to encryption. I will show you 3 different ways of encryption and share some recommendations on best practices. Let's start by looking at the sample code I've created. Here we have encryption algorithms class. The first encryption utility is cipher encryption. The idea behind the cipher is very simple. It uses a number called shift to transform letters and sometimes numbers into other characters based on this shift. For example, if the shift is 3, the letter A becomes D and the number 1 becomes 4. This method of encryption is extremely simple and therefore it is very easy to recognize and decrypt it. I've added it to my demo just to show it to you as an example. It should never be used in production applications, although in my experience I have seen this cipher in low quality Android applications. Next, we have the AES encryptor utility. AES stands for Advanced Encryption Standard, and it is a modern encryption method which is considered to be the current standard for secure encryption. It uses a key and IV, initialization vector, as parameters to encrypt and decrypt strings. Now let me show you how encryption works in my main class. We have a sample string here, it's a Wikipedia URL. We will encode and decode it using both of our encryption methods and then check the results in the logs. So let's launch the application and take a look. As you can see, cipher encryption is quite weak since we can still tell that it is a URL just by its structure. Yes, the cipher could be improved to include characters of all types, but it would be still recognizable for an experienced reverse engineer. If you look at the AES encryption results, they appear much stronger and more secure. We cannot understand anything from the encrypted strings. I've shown you examples of both encryption and decryption. However, when reverse engineering applications, you will typically see already encrypted strings and the method to decrypt them. So to give you an example close to real-world scenario, I've created a sample application with some simple encryption logic. I haven't used obfuscation here to keep everything clear for you, but keep in mind that developers, especially malicious ones, will try to hide something and the code will usually be obfuscated and encrypted at the same time. So here we have a main activity class and let's take a look at it. We can see two methods that handle the logic of setting text in the text views. The strings being set are actually the results of methods from another classes. Let's follow one of them. When we open that class, we can see several strings, all of them encrypted. And notice that they are all passed to the decrypt method of another class. So let's open that next. Once we do, we can see the full decryption class logic. Once again, in a real-world scenario, the code would almost certainly be obfuscated, and we wouldn't see the class name as clear as here. However, even if the class name was hidden, we could still understand it's related to decryption. Its method is used for multiple encoded strings, and we also can see the logic involving numbers and symbols, which is a strong indicator of decryption functionality. For an experienced reverse engineer, even without the class name, it would be immediately recognizable as Keyser cipher, mainly because of this line. The mod 26 is a clear sign of Keyser cipher logic, since 26 is a number of letters in an English alphabet. And here are two ways how we can proceed in this case. First, let's just open our browser and find Keyser cipher decoder. We copy any encrypted string from the code, and then we also notice the number 7, which indicates the shift. On the website, we choose the decode option, set the shift to 7, and paste our string. And here we are, we can see the original string, which is a URL. The second way to proceed with decryption, which would also work for any weak or poorly implemented encryption method, is to recreate its logic in our local environment. First, we proceed to JDEX and fully copy the class responsible for decryption. We return back to Android Studio and paste all this code there. However, you can see some errors because the compiled code often uses some synthetic methods. However, we can easily fix it manually. In this case, we just need to remove the $default part and change some arguments passed to the method. If you are not sure how to fix such conflicts, you can always ask AI helpers to do it for you, and it's completely normal practice. So now our class is ready to be used. So we proceed to main activity, and just inside the onCreate method we call the decrypt method for our new class. The arguments for decryption we take directly from JDEX. Let's copy them from the first method call. And of course we need to put the output to the logs so we can see the result. Now we are ready to launch our app and check the output. Let's start it. And as you can see, we successfully decrypted the string again. We can repeat this process for other strings. Let's do it to see them all. In a real-world scenario, there may be hundreds of such strings, and it would take a lot of time to copy them manually. For such situations, some scripts may be used to extract multiple strings automatically, but that's a topic for a separate video. For now, we will copy them manually. So we are now ready, and after launching the app again, we can see all the strings successfully decrypted. This method works well when the decryption mechanism is weak or implemented insecurely. There is one more way of decryption, and it is actually one of the most reliable ones, and it's using Frida. However, we will cover Frida in following videos, and now it's just for your information. Now let's consider another decryption class that we have in our sample APK. We proceed from main activity to the class that uses it, and we can see that it decrypts strings using another helper class. We proceed, and from the name we can see that it is AES encryption. However, we could also understand that even without the name of the class, since in the body of the decrypting method we can see the usage of AES related strings and functions. AES is a standard encryption method, and if it is implemented correctly, it's practically impossible to decrypt it. However, here I've made an example of bad implementation so we can immediately see the key. Having the key, it becomes easy to decrypt AES if you understand the process. To decrypt it, we will use a very powerful tool called CyberChef. It's an open source tool that allows you to perform different operations with strings and files, including encryption, encoding, and much more. Before we start, I have to quickly explain you how AES encryption works. It requires two main parameters, the key and the vector. The key is the secret password that both sides must know. It's used to lock and unlock the data. Without the correct key, you cannot read the message. The vector, which is called IV, initialization vector, acts as a random starting point. It ensures that even if you encrypt the data twice with the same key, the results will be completely different. Then AES takes your data, such as text, files, or passwords, and transforms it to an unreadable code using several rounds of substitution and mixing. The result is called cipher text, which looks like random characters. When you want to read it again, AES uses the same key and vector to reverse the process and get your original data back. So to decode AES, we will need the key and an initialization vector. To get the IV, we take any encoded string and extract it directly from the bytes. In my implementation, you can see that before all operations, the encoded text is base 64 decoded, and the IV is the first 16 bytes. So we copy an encoded string, open browser and search for CyberChef. We open the official page and wait for it to load. CyberChef is extremely useful tool for reverse engineering and string manipulation. To build the recipe, we search for from base 64 and drag it into the recipe field. The IV will be the first 16 bytes or 32 characters, so we copy that slice. Next we search for AES decrypt and add it to our recipe. We paste the copied IV into the IV field and set it as base 64. As you remember, the key is present in the code, which is actually a bad practice. So we copy the key and paste it into the key field using UTF-8 format. CyberChef will output the decoded string. The initial gibberish bytes you can see is the IV, and the remaining bytes are the visible plain text. On the other hand, we can also repeat the process locally like we did with Keyser example. Let's copy the AES decryptor class from JDEX and create a custom Java class with the same name in Android Studio. In this demo there are no conflicts, so we can launch the code straightforwardly. Now we are set. We launch the app to check the logs. And as you can see, all strings are successfully decrypted. So that's how encrypted strings may be recovered from reverse engineering perspective. The examples above show you bad practices, which makes it relatively easy to decrypt the sensitive data. The best practice is either to use Android key store or to perform server-side decryption when it is possible, so no secret is present in the client side. Okay, now let's move further. As you remember, I have said I will show you 3 encryption methods, but actually showed only 2, Keyser and AES. That is because the third method is more specific. It is done via an imported library called StringFog from GitHub. With this library, you write strings in your APK normally, and the library transforms them so they are stored encrypted and then decoded at runtime, typically using lightweight operations like XOR. Let's check on an example. I created a sample application with several hard-coded strings across multiple classes and added StringFog dependency in build Gradle. After decompiling the APK in JDEX, we proceed to main activity and see that the strings are now obfuscated and encrypted. All strings across the classes were automatically transformed by the library. This library is fairly common to make static analysis harder, but it's not fully reliable. You can usually decrypt its strings by copying the library's runtime decryptor and running it locally, like we did before. Or you can do it even easier by intercepting it with Frida. In practice, StringFog is used more as an obfuscation layer than the cryptographic protection. Combined with the code obfuscation, it raises the bar, but it should not be relied on to protect critical secrets. So that's it for encryption, and now we can proceed to examples of encoding. First we will look at base 64. Base 64 is commonly used to store binary data in text format. For example, embedding the image, storing credentials, or including a key in a JSON. It's simple to use and very common in apps. Some developers encode strings using base 64 to make them less readable during static code analysis, but it doesn't provide any real protection. An experienced reverse engineer will recognize base 64 immediately. For example, URL encoded in base 64 will start with these symbols, which means HTTP. Now let's check URL encoding. This is used when URL contains reserved characters, such as spaces or non-SCI symbols. URL encoding replaces this with specific % sequence so that the URL can be transmitted safely and opened by servers and browser. And one more type of encoding is character encoding. This defines how text characters are represented by bytes. The most common and recommended encoding for symbols is UTF-8, since it supports all languages. When encoding is mismatched, you will see just gibberish and unreadable text. Now when we know what encoding is, let's look at it on practice. I've created a small application with examples of encoding and decoding, and used base 64, UTF-8 and URL encoding. Let's go through the code step by step. At the top, I have 2 sample strings, a URL and a text that includes English and non-English characters and emojis. That way we can clearly see how different encodings handle both normal and specific characters. Here I first encode both strings using base 64 and log the results. Then I decode the same strings back and log them again. So in the logs we will see 2 encoded values and then 2 decoded ones, making it easy to compare them before and after. Next we move to URL encoding. We have here the same flow as with base 64. And finally we proceed to characters encoding, and this part is especially interesting. Here I convert the string into bytes using the UTF-8 charset. Then I log the raw byte arrays to show how the data actually looks in binary form. And after that I decode those same bytes twice. once using the correct char set UTF-8 and once using the wrong one, ISO. This helps to demonstrate what happens when the app uses the wrong encodings. You get broken or unreadable characters. And just like before, I log everything. Now let's run the app to check the logs together. First, the base64 section. We can see the encoded URL, it looks like random letters and numbers, and the same with encoded text. Then we see them decoded back to their original readable form. So base64 doesn't hide the data, it just changes how it is represented. Anyone can decode it back easily. Now let's check URL encoding results. The encoded URL looks like this, and the encoded text has those long sequences representing Cyrillic letters and emojis. This is how URL encoding safely carries any characters across the web. But again, it's not encryption, it's just formatting. And finally, the characters encoding section. Here we see the raw byte arrays for UTF-8, each character represented by one or more bytes values. When we decode those bytes correctly with UTF-8, the text looks exactly as expected. But when we decode the same bytes using ISO, we get broken characters like this. That's what happens when the wrong char set is used. The bytes are fine, but the interpretation is wrong. And before we finish with encoding, let's also take a quick look at CyberChef again. As I have shown you before, CyberChef is a universal tool that handles all transformations of data. You can easily decode everything we saw in this demo just from your browser. Let's check it quickly. We copy our base64 encoded string, open CyberChef and drag the from base64 operation in the recipe field. After that, we just paste our encoded value in the input window, and instantly we can see the original text decoded at the right side. No key, no passwords, no tricks. It's just automatic because encoding is always reversible. The same goes for URL encoding. If we paste the encoded URL and choose URL decode, CyberChef immediately shows the readable text again. It's a great example how tools like this make encoding extremely fast, and also why encoding should never be used instead of encryption. And finally, let's test char set encoding. If we paste our UTF bytes or text and select the decode text operation, then set the input encoding to UTF-8, we will see the correct text appear. But if we change the encoding to something else, for example ISO, you will immediately see the broken characters appear, just like in our logs and application. So to summarize, encoding is all about compatibility, not security. Still, as a reverse engineer, you will often see encoded strings when analyzing applications. Correctly recognizing the encoding format can save a lot of time for you. And with experience, you will immediately recognize all encoding formats easily. And now let's proceed to hashing. Hashing is a one-way transformation. It takes any input like text, file, or bytes and produces a fixed length output called hash or digest. Unlike encryption or encoding, hashing cannot be reversed to receive the original input. Even a tiny change in input radically changes the output, which is called avalanche effect. For hashing, I've also prepared a sample code to see how it works. In this demo, we compute SHA-256 for a string, then change just one character and hash it. You will see the digest completely change. I'll also compute MD5 to show the difference. It's fast and short, but it's not secure anymore, so don't use it for any protection. And finally, we compute an HMAC SHA-256 using a secret key. With the same message but a different key, the HMAC changes. This proves that HMAC provides both authenticity and integrity. If the key is hard-coded in APK though, the attacker can recompute valid HMACs, so don't keep the secrets inside the APK or keep them in a key store. So what do we see in the logs? We see SHA-256 for a sample text. This is a 256-bit digest of the original string. It's fixed length and looks random. We also see SHA-256 for sample text plus dot. We changed just one character, added a dot, and the entire digest changed. That's the avalanche effect in action. We see logs for MD5 for a sample text. MD5 is much shorter and very fast, but it's not secure for anything sensitive. This can be used only for non-security checksums. And we also see HMAC SHA-256 for a sample text with one key. And we see another log for HMAC SHA-256 for sample text with a different key. And with the same message but different key, we see the completely different output. This shows that HMAC depends on the secret key. And quick summary for hashing. Hashing is not equal to encoding or encryption. It's one way and cannot be reversed. SHA-256 is good for integrity checks, since it detects changes. MD5 and SHA-1 are outdated, and avoid using them for protection and security checks. HMAC SHA-256 adds a secret key, and it's good for integrity and authenticity. So to quickly recap on everything we have talked about. Obfuscation is about hiding your code logic to make it harder to read and understand. It's technically reversible, but not really worth these efforts. Typical examples are ProGuard, R8, or custom naming. Encoding is only changing the data format so it can be transmitted or stored safely. Typical examples are base64, UTF-8, or URL encoding. It's always reversible and is not meant for security at all. Encryption is about protecting data from unauthorized access. You can reverse it only having the correct key. Examples include RSA, AES, or even some simple ciphers like Kisser. And hashing is one way, and it's used only to verify data integrity. You cannot reverse the hash, you can only try to guess the original input. Common examples are SHA-256 or bcrypt. So, in short, obfuscation hides logic, encoding changes format, encryption logs data with key, and hashing creates a one-way fingerprint. And that's it for today. We walked through obfuscation, encoding, encryption, and hashing. What they are, how they differ, and how they look from reverse engineering perspective. If you liked this video, please put your like and subscription, and hit the bell so you don't miss the next video. If you have any suggestions or ideas, please drop them in the comment section below. Thanks for watching.